So while our first speaker just sets up their screen sharing, so Stefan, you can do that now, I'm going to introduce them. So to begin our workshop, we are delighted to welcome Professor Stefan Leutenegger. Stefan is a senior lecturer or associate professor, as it's called in the US and Canada, in robotics at the Department of Computing at Imperial College London. There, Stefan leads the Smart Robotics Lab and also co-directs the Dyson Robotics Lab. Along with his group and collaborators, Stefan has published a number of highly influential papers in the broad areas of SLAM and visual localization, including, and I'm sorry, Stefan, I don't want to embarrass you, but I had to name drop a little bit, BRISC, binary, robust, and variant scalable key points, as well as keyframe-based visual inertial odometry using nonlinear optimization, both of which were highly influential in my own PhD, and also more recently, dense SLAM techniques such as elastic and semantic fusion. Stefan has also co-founded SlamCore, a company aimed at the commercialization of localization and mapping solutions for robots and drones. Finally, he received his BSc, MSc, and PhD from ETH Zurich, and his PhD was entitled Unmanned Solar Airplanes, Design and Algorithms for Efficient and Robust Autonomous Operation. So without further ado, please join me in virtually welcoming our first speaker of the workshop, Professor Stefan Leutenegger.
Okay, well, thank you very much, Valentin, and everyone for inviting me here. I think it's a really exciting workshop and a very nice program around the subject. So let me talk about robustness in mobile robotic perception and action as a sort of general topic, regarding also power on and go robots, of course. So let's see if that works here. Okay, so I was just going to show this example first, because this is the closest thing to a power on and go robot that I've ever built in my career so far. It was for this Embezirk challenge, where we had to build a drone and equip it with the right algorithms and software to, after one button click that was only allowed, it had to take off, go find a moving vehicle on the ground, and then land on it. So we put together this kind of drone with relatively off-the-shelf components. There is a visual inertial and depth camera there and a real sense. So we wanted to do all of this actually with onboard SLAM rather than GPS or so it works also indoors. And then there's this downward-looking camera that was going to spot this moving vehicle. And of course, all the processing had to be done on board. You saw there an Intel NUC that did all the processing there. So we were running visual inertial SLAM, sent it to a kind of position where we were expecting that the ground vehicle was going to pass through. So all of that was quite precisely set up and known in advance what was going to happen roughly. So we could kind of engineer things around that, and then, you know, kind of tracking this moving vehicle on the ground and approach and land on it. And here's the tricky bit. This is all about robustness that I said, right? So you need to make this work not just once, but in all kinds of different environmental conditions. And to tell you the truth, in the actual competition, we weren't very successful. And it was precisely because we didn't put in enough effort to really make this work in a robust enough way. We just, you know, we ran out of time, and testing in London is difficult. But then we fixed it afterwards, and we made it robust. And that's what you saw there. And it's quite a fair amount of work that you have to put in. Okay, so this was, you know, a quite classical robotic system otherwise, visual inertial SLAM, and then it was using model predictive control to control this thing. But let me talk a little bit about the sort of space of where we have, you know, successful or maybe not so successful yet robotic applications. So I kind of put this into the kind of two axes here. One is the dimension of the complexity of the task that you're trying to solve. So really quite narrowly specified tasks on the left and very open-ended complex kinds of tasks on the right. And the other dimension is around the environment. How specific, how controlled is the environment? So quite specific on the bottom and quite open-ended on the top here. And so the example that I've just shown is very much, I would say, sort of towards the left, right? It's a very clearly, very narrowly defined task. And then so I would argue this is why, you know, we could make it work with the necessary engineering that still need to go in there. You can kind of make it work, maybe not perfectly, but it kind of works. And similarly, you can see a lot of robotic applications that are working in the sort of left part of this chart and in the bottom part of this chart. You know, vacuum cleaners and assembly lines, of course, we have had for a long time. But increasingly, I guess we can see a shift towards things that are becoming feasible also towards the right, where it's a bit more interesting, more open-ended kind of tasks that we can solve. But this kind of combination of both open-ended tasks as well as uncontrolled open-ended environment, I think that's still where we're still quite far away from real-world applicability. There you find things like autonomous driving, like delivery drones, the kind of things that we are expected to come up with as roboticists quite soon, but where I think there's actually still a lot of work to be done, such that we can have power on and go robots in that space. So maybe just a little bit why I think this is the case. Why do we still have these issues? I think a lot has to do actually with robustness ultimately. We can get these things to work in some circumstances, some environments, some tasks, but just not quite as robustly across the board. And why is that? So if you look at the sort of classic cycle here of perception and action, you see the typical kind of modules that we build, right? And you have more the perception side on the left, you have then more of the kind of task planning and control side on the right. And this is the kind of classic modular thing that we would do, and this is to some degree what I've shown in the first example as well. Really, this has a lot of advantages, of course. You can modularize this system, you can introspect it, you understand what's going on. You share the same kind of concepts as a user, as a roboticist, to see what's going on, to instruct the robot, and that's all good. But at the same time, I would say the main problem that we get with these kinds of systems is actually right in the middle there. There's a gap. And maybe not just there, maybe just more also generally between these different modules, you have to somehow distill some form of a representation, some form of an estimate of what's going on, and you have to pass that on to the next module. And if you're making mistakes, then that's where things can break down quite easily. So you have these kind of gaps. So of course, it's then very appealing to kind of try to get rid of these gaps and go with a very much more black box kind of approach, where you learn how to map sensing into action, for instance, with deep reinforcement learning. So you can literally get rid of these kind of bottlenecks that you have here in a more classical system. So that's elegant. You have to do less handcrafting. But at the same time, I guess we come to the conclusion now that there's also quite significant issues with that. We have a lack of guarantees. These are difficult to introspect what's going on. But I think actually the main issue here really is that when you go towards the upper right corner of my previous diagram, the kind of more open-ended tasks and environments, then simply this kind of learning-based approach in this very much black box ways is not going to be data efficient enough to learn these kinds of more interesting applications where you might want to, interact with real people and so on. So that's where you start to hit the bottlenecks there. So I think we're sort of converging to some models of bringing in learning approaches into these different modules that we have in a maybe more traditional system, or maybe it's a bit the other way around, depending on what end of the spectrum here you're sitting, that you bring in modules in a sort of more end-to-end learned kind of approach. So that's what my task is going to be a little bit around, like how can we mitigate the current shortcomings of these systems by kind of bringing these things together and achieve more robustness. And as Valentin has already kindly introduced, so a lot of my work has been sort of in this space of, let's say, spatial AI or different levels of spatial AI. So, I mean, this is of course collaborations with a lot of people back at Imperial and at ETH, working on visual inertial localization mapping with OCVIS. So this was more a focus on sort of the very basics of just position orientation, rather than probably the map. And you can do a certain amount of things with it, like flying over flat terrain. And then, where there's more of an interest in dense geometry, allowing for motion planning, collision avoidance, and things like that. And of course, what I'm very interested at the moment is how to bring in deep learning, how to bring in semantic understanding of the scene to really allow for more advanced kind of task planning and interaction with a human that could, for instance, instruct here a vacuum cleaner to go clean the floor underneath the bed, for which you really need both the notion of 3D space as well as semantics. But clearly that's also not going to cut it for the more complex kind of things you might want to do. So we have to move up the levels here and go towards more object level, also dynamic kind of maps, and clearly shouldn't ignore the human all the time. So we have to also be aware of humans, what they are doing, what they're up to, where they are, and so on. So that this is very much you know, an open area of research, of course, to move up these levels here. So I'm just going to give a quick overview of some two elements here of dense mapping and object level semantic maps in the next couple of slides. So one of the kind of central questions around dense maps is then, what is actually the right representation? What is this thing that should go in there that is being passed around between the modules? How do we best represent stuff in the context of robotics? And I think it matters really that this is in the context of robotics. I mean, computer vision has been proposing different kind of things here. It's often about precise surfaces that are precisely described somehow. But I think as roboticists, we have to really ask the question, what is the right thing for the task? And there's probably not one answer, but I think a very useful one is really a kind of volumetric one, where you don't explicitly represent surfaces, but where you explicitly represent something like occupancy or distance from surface. So you can use TSDF, truncated time distance fields, or logODS occupancy values that have proven very useful, I would say, for then robotic planning. So this is what I'll be showing in the next couple of slides as a kind of popular representation that we have been adopting, where then you have a zero crossing of this function that actually represents the surface. But first and foremost, you have to encode these values in space everywhere. And of course, there's a question, how can you do this efficiently? We've worked a lot recently with octrees as kind of volumetric hierarchical approaches, which have the advantage of being efficient, of course, memory efficient also for data access. But I also like the kind of hierarchical nature because it integrates nicely with this concept of adaptive resolution. You always have this problem that stuff that is far away for a camera is appearing smaller in the image, and you should somehow reflect that. And so what we were using here is exactly this kind of hierarchical representation is adopted in both the tracking stage. So you can use ICP-based tracking, for instance, against this TSDF or logODS occupancy field, as well as in the integration of new information. So we can now kind of slide between different levels of detail and really select the one that is right, such that you can avoid aliasing artifacts in the integration here, as well as you can actually be more efficient because you can access data at a higher resolution when it's further away. You don't have to traverse all the way down to very fine resolutions. So that has actually proven an interesting concept that helps us in terms of generating accurate maps. So here's a kind of dense map representation that we can create like that. And you can see the color denoting here the kind of level of resolution that we are selecting. So red being the sort of next coarser resolution, green the finest resolution, and blue the coarsest resolution. You can also adopt this concept then for actually integrating fusing color and create these nice kind of colored maps. Okay, so this has allowed sort of higher accuracy, as you can see here, towards the baseline kind of Kinect fusion, single resolution type implementation. So you can really see the differences that you get nicer details like this. And also it helps in terms of speed of integration and tracking because of more efficient data access and less manipulation you have to do, especially when stuff is far away. So I've been able to show this is actually bringing quite significant speed ups between, the green being the multi-resolution here and the red being a baseline octree-based fusion approach, but at just the finest resolution without this adaptive resolution approach. Okay, so maybe then a bit more interesting, you can actually start to use these kind of representations also to move up the levels and go towards object level semantic mapping. So this is now a system that we put together called Midfusion, is decomposing the scene into what is actually movable kind of submaps per object submaps. You can see the reconstruction in the center here, inputs on the left, and the kind of semantic instances on the right as well. So of course, now this is where you bring in deep learning. This is how these kind of things can be engineered. And for some reason, it has now stopped playing. Okay, let's keep going here. Okay, so you see on the bottom line of the kind of pipeline that we have, where we do tracking of the camera. So it's still a SLAM system. We don't know where the camera is. Tracking of the camera sort of with respect to the static world, but then also tracking individual objects, as well as fusing and mapping these individual objects as well as the background. So we are assuming no prior kind of object knowledge in this kind of work here, which is, it's a bit unreasonably difficult probably as a problem, but we wanted to see how far can you go without previously knowing objects or anything about the scene. And then on the top here, you have the stream of actually processing frames with what this is in this case, mask-R CNN, to give you initial object proposals and segmentation masks and so on, to bootstrap the whole kind of segmentation into individual map objects. Okay, so here's just a quick example of how this works. Also with several objects that can be pushed around, and you can see how this could be really quite useful to do manipulation of several objects with these kind of explicit 3D representations. But it's clearly not perfect, right? I mean, it looks nice in this video, but there are imperfections, and in practice it will still fail. So there's clearly a lot more work to be done to make this make this part of a power on and go robot very clearly. Okay, all right. So let me now, however, move back to drones, back to also maybe how we can use some of these spatial AI technologies inside a full mobile robotic cycle here. So the first example I've shown with that Bezirk drone that was landing was this architecture above. This is the kind of control architecture above, where you actually have an inner control loop that controls the attitude of the drone, and then you use linear model and linear model predictive control to control this thing around. And I mean, it's good enough to do a lot of things, especially the application at hand. But more recently, we've been trying to see what you can do with NonLinear MPC, where you eliminate this kind of inner control loop, and you directly try to optimize for rotation speeds, and we can now use the fully nonlinear identified model to directly control the drone and the individual motors. So then, of course, you still have to actually identify the parameters, but that's what I think is nice. So this is, maybe you can characterize it as learning or calibration or just parameter identification. It's all similar, but the important bit is that it's relatively low parametric. So you have a couple of constants here that you need to identify in a short flight. Could even be just after takeoff, right? And then you're good to go. You have a model that generalizes across any kind of thing you might want to do with that drone ever. So that's what I like about it. And then you can go into nonlinear model predictive control, the classic kind of fixed horizon cost function that you can optimize, penalizing different things in here, position, yaw, velocity, and find the solution at runtime. So you can see how this works here with our drone in our arena. Playing this. This was ICRA this year. So we give us a step command here in yaw and position. And what you saw, this kind of weird flip is not some learned or specified behavior. This is like a kind of self-emergent behavior that the drone has never seen or done before. And it just comes out as the most efficient thing to do this kind of maneuver. So that's quite interesting, I think, for a power on and go system, that there's no kind of specifics, no learning. You can also do inverted flight. I mean, here we have actually managed to be able to have the rotors invertible, the directions invertible. So you can use the very same controller, very same model to do inverted flight. You can also disable one of the motors. And because it's invertible directions, you can show that you can still both experimentally show as well as theoretically show that you can still keep the orientation completely, all the 6 degrees of freedom. And what you can see here is actually we can also detect, again, model-based. Once the model is identified, you can detect when something goes wrong and the motor stops. So that's really addressing the robustness again here, right? And you have to be quick. So you can pretty quickly detect here what's going on, that is actually stopped. And we can make the necessary corrections and still get the drone fully controllable and can take it back to a safe home position. So this also doesn't just work in hover, it also works when you do set point commands. So we can detect immediately something's gone wrong, switch it off, and keep going. Okay, and then you can move on to a safe landing. All right. So again, here, that's good for the robustness, right? This is important, I think, for a real-world system. But also, you have to make sure that this kind of detection itself is a robust thing to do. You don't want to have constantly false detections or misdetections. So we show here actually 16 successive experiments where it's all detected things correctly. Right. Now for the final example, just briefly, as I'm running out of time, we have used the same kind of nonlinear controller architecture and augmented it also with a little delta arm here that Dimos, the PhD student I was working on, has built, custom built. So it's a kind of, again, low cost system. We wanted to see how we could manipulate with a relatively standard hexacopter here and actually write something on a whiteboard in this case. So we just augmented the control architecture a little bit by now also penalizing here end effector lateral position as well as contact normal force. And so in this case, you can have this kind of hybrid cost function that again is just fitting naturally with then the nonlinear model predictive control scheme. So let me just show this video then finally. This is how it works. Drone approaches the whiteboard, goes ahead and writes something on it. And what I should say though is that while this is in some sense, it is a power on and go system, but it is still really quite engineered, right? That the drone needs to know quite precisely where this whiteboard is. We're using the Viken motion tracking system here as well to really get that working. So clearly there is a lot of scope for bringing in the kind of spatial AI side of things, for bringing in some forms of online parameter estimation to really make that work in a less controlled environment and to move these kind of applications further towards the sort of upper right corner of my initial diagram. But again, it was hard enough to get this to work. We wanted to have both the accuracy as well as the robustness of doing this. So just to show you here, there's a couple of subsequent experiments with variations in speed, just to show that it doesn't just work once, it can actually still work in different circumstances and in subsequent experiments. All right, I'm out of time, so I'm also finished actually. So thank you very much for listening to my talk. And I don't know, maybe you have time for 1 or 2 questions.
I think we do. Thank you very much, Stefan. I'm gonna do a little virtual clap. I think I have a sound effect here. I don't know if you can hear. There we go. All right, so we do have time. We have about 5 minutes. We forgot to announce that it's going to be, so each speaker is going to have 20 minutes and then there'll be about a 5-minute block for questions. So please go ahead and you can put any of your questions in chat. We do have one from one of the attendees, from Mohammed, who says, for Dr. Leutenegger, can we constrain the NMPC controller to avoid certain undesired behavior?
Yes, this is a good question. I guess it depends on what we mean by behavior. So we already use constraints here. We use state constraints, for instance, to avoid certain undesired configurations, and also soft constraints to in principle avoid certain states that would be undesirable. For instance, self collisions of the the manipulator or things like that. In principle, also we could use collision constraints, for instance, with the environment. That could become more and more complex. I don't quite know. I mean, it's something we're exploring now. How complex you could make it, to what extent we could really use a very detailed description, dense environment description, just as state constraints to let this thing avoid collisions. So in principle, I think a lot of these things are feasible. If you mean more abstract behaviors, then of course that becomes more difficult. That's where we still need to then specify what that actually means, how it translates to some constraints in a controller.
Mm-hmm. Okay, and maybe one more high-level question. I'm gonna sort of jump off. Well, actually, no, we do have one more. I was gonna do a question from the organizers, but we can talk later. So we have a question from John. So thank you, Stefan. Great talk. For the landing on a moving target UAV, what did you do to make it more robust?
Yeah, good question. I think it has to do a lot with testing in the end, because you think you have a very nice system in the beginning and then you test it first. And it's exactly like in this kind of initial description of the workshop, right? You turn it on and it doesn't work. So because just there are so many things that we don't think about. So yes, I think the trick is really to test, and there's no single answer then to how to make it more robust. There's a lot of different fixes here and there. You have to address things like illumination invariance in the images, to look at different image processing steps there necessary, for instance, to always track the moving vehicle. But there are other things that you don't think about that actually hit us, like when you're being too aggressive with trying to follow the moving target, then your moving target goes out of the field of view. And so you need to engineer around that. So you might restrict your roll and pitch angles. And even though you give up some aggressiveness of your drone, you can keep better in field of view your target. And I mean, maybe we should have had a sort of higher field of view camera in the first place. And then you try to work around that or try to kind of fix that. I mean, there's an unlimited amount of things that you figure out and fix. The thing is testing, yes. I mean, it really requires quite a lot of time testing and engineering around it. And I mean, this is maybe something we can discuss a bit in the discussion later on, is how much engineering and testing is reasonable for us to do as robotics researchers. I mean, this probably hit, this project showed initially probably hit a bit the limit of what is reasonable for a robotics research lab. But it's still important in many ways, of course, to do it, to make progress, to actually show stuff works.
Okay, that's great. And thank you very much for advertising the panel as well. So if you have any more questions for Stefan, he will be joining our panel discussion towards the end of the workshop. So I'd just like to thank Stefan one more time. Thank you very much.
Okay, thank you very much.